Hi, everyone. This is a presentation on NEM management about the service lifecycle upgrades, API, and tools. Most of it is Scott. I have a tiny little section in the end. So with that, take it away, Scott.
This presentation is NEM management on service lifecycle upgrades, API, and tools. We're going to kind of try to cover a lot of different topics very broadly. So first of all, what is the NEM? The NEM is, the acronym stands for Network Edge Mediator. You can think of it as the topmost layer of the SIBA pod. It's kind of the glue layer that exists between the operator's OSS, BSS systems on top, the various use cases the operator's trying to do, mobile, enterprise, residential, and the services inside the SIBA pod. It is where we implement our FCAPS components. It's also where we handle lifecycle management of the pod. So our vision is that SIBA pods will be long-lived, and since they are long-lived, the service sets on these pods may be dynamic. So you may upgrade services over time, and you may even add new services over time. Because the pod is dynamic, we expect that it needs to be extensible. The core data model needs to be able to evolve to have new service models and new workflows introduced. So the NEM, since it is that topmost component and it is that API abstraction, it manages the pod and it manages the service stack within the pod. So it configures ONF apps, for example. It configures subscribers. It configures the whitelist of what residential subscribers are allowed to have ONUs and the serial numbers and where they can be attached. All of that persistent state is inside of the NEM. So managing the pod directly means managing the NEM because you want to manage all that stuff. To manage the NEM, we break it down into two parts. One of them is a service management component. We have all of these different services. For example, we have a virtual OLT service. We have a fabric service. All of these services need to work together, yet they're implemented independently, each with their own APIs and abstractions. So the NEM bridges this gap between services so that those services can cooperate and present a unified interface to the northbound consumers, the operators. Now, there may be abstractions that span multiple services. So for example, a subscriber is a concept that touches many different parts of a pod. A subscriber has a presence in the virtual OLT service because a subscriber has physically an ONU, but a subscriber also has a presence in the fabric because that subscriber's packets need to pass through the fabric out to the broadband, out to the BNG and out to the internet. And the northbound consumers we expect want a uniform interface, and I will talk about that in another slide or so. Now, that is the sort of software service management aspect. There's also a container management aspect, which is that all of our software does run in containers. And because it runs in containers, we use standard container-based tools, things like Kubernetes, Docker, Helm, your usual cloud containerization tool set. And I believe Zack will talk about that a little bit later in the presentation. I'm going to spend most of my time talking about XOS. Now, it's important to note that some concepts span container management and service management. So for example, to upgrade a service, you're probably replacing a container, but you're also perhaps updating the service modeling at the same time. So a lot of these concepts will span both of those aspects of management of the pod. So one of our key things when we developed XOS was the goal that we present a unified interface. And why is a unified interface important? Well, it's important because we have a bunch of different services and we disaggregated them. When you disaggregate them, they tend to become somewhat semi-independent. And at the top, we also have a bunch of different consumers. We didn't want the N times M case where every consumer needed to implement special purpose logic to talk to every service. So we envision XOS as kind of the unifier to take all of these disaggregated components and put them under a common API that is easy for the consumers to integrate to. XOS is gRPC based. It presents a gRPC interface northbound for the operators. and it allows various services to be plugged in southbound of XOS, and we'll see how that works in a moment. And just to illustrate this N times M component, we have all of these different partners, operator partners at the top that all want to use the SIBA pod. And then we have all of the different services at the bottom. So all of those different use cases, all of these different building blocks to avoid the pairwise where everyone has to understand every building block, we put the NEM and furthermore XOS in the middle. And we call that our extensible platform since it's designed to have more services added to it over time. During the next set of slides, I'm going to kind of drill down into XOS. I'm going to cover kind of the macro architecture of where XOS fits into the NEM. I'm going to cover a little bit of the core architecture of XOS, and I'm going to talk about the XOS data model. So the XOS macro architecture. So XOS is a set of containers. Do we have, okay, so our pointer does work. Oh, well. So we've got these here containers are kind of the service independent portion of XOS. They're generalized data model containers. You can think of XOS as wrapping a database. The database in this case is Postgres, although that is pluggable, so you could imagine using other databases than Postgres. So XOS wraps Postgres and provides some northbound interfaces. The northbound interface to XOS is gRPC. And you can come over here via this arrow, and an operator could interact with XOS via gRPC directly. Or we have some translators. We have Chameleon and a Tosca engine that sit on top of XOS. Chameleon is a REST to gRPC translator, so anything that we export on the gRPC API, Chameleon automatically translates it into a REST API. The Tosca engine is for running Tosca recipes, so it lets you specify a list of Tosca nodes and entities, and it will take that Tosca recipe and execute the appropriate gRPC operations in XOS. Tosca is how we typically provision a pod to configure the service chain and such. Now down here at the bottom, I have put a bunch of synchronizers. Synchronizers are what you can think of as the service-specific portion of XOS. If this was Volta, you would possibly call a synchronizer an adapter. It's the same sort of concept. You take the general purpose XOS and you specialize it to a particular service. Now these service synchronizers, they typically contain model extensions. So for example, the RCord subscriber service will have a subscriber model in it, which it will contribute back to the core, and the core will update its data model to include that model description. I should emphasize that these are synchronizer containers, not services proper. So for example, you will see an ONF synchronizer. That is the XOS synchronizer that speaks to the ONF service, not the ONF service itself. So every service that you want to integrate with XOS, you typically implement one of these synchronizers. Looking inside that middle blue box, the XOS core, it's kind of broken down into several pieces. As I said before, it is a gRPC server, so at the very top of it is a gRPC server layer. Beneath that, there is some security infrastructure. We have an entire role-based security access where we have user accounts that are allowed to perform XOS operations. And then we have roles and we have bindings between the user accounts and what objects are allowed to touch. So we can partition up the management aspect of a pod into different people who are allowed to do different things. So the security layer would handle that. Beneath that, there is the data model itself. The data model is built on a Python component called Django, which is a popular object relational data model for Python. And it will, Django has several different backends. You can select which backend you want. We have chosen the backend engine to use Postgres. So you'll see we connect to a Postgres database. Now to configure the data model, we have something that we call xproto. And I will show you a couple of examples of xproto in a moment. So xproto is our specification language. You submit xproto declarations to the core, and the core configures the data model and in turn configures a schema in the database. We also make a lot of use of Kafka. So there is, Kafka is used in two contexts within the XOS core. One is as a destination for logging. Whenever there's a noteworthy log event in the core, it will send it out to Kafka where it can be collected via our FCAP solution. There is also a notification mechanism. So whenever a model changes in the core, it will post an event on Kafka that lets you know that that model and a particular field within that model changed. That's used, for example, by our GUI so that the GUI can automatically know to update its visual elements. It's also used sometimes for components to talk to one another. So a component could post a Kafka event and another component could read that Kafka event and know that something has changed. So drilling down to the next layer, the key thing that XOS implements is this data model. And as I said before, it is a traditional relational database based on Django. And Django, furthermore, in our case, using Postgres. We have extended it a little bit. For example, we have a notion of inheritance, that one data model object can inherit the definitions of another. We use that a lot. I will go through some xproto examples in another slide or two. The data model contributes lots of base models, so we have, I don't know, maybe a dozen or two base models for things like users, permissions, compute resources, network resources, sites in case you have multiple sites where multiple pods are deployed, that sort of thing. So there's a lot of value comes built in. There's also a notion of services and a notion of tenancy within services that are built-in concepts in XOS, and the notion of dependencies between services. So you might have two services, one that requires the other to achieve its work. We tend to put these services and tenants in chains. So a subscriber might have a chain that will go through several services, and I'll illustrate with a picture. And in addition to the base models, our key contribution is this extensibility. And extensibility is value that you can add. So any service can contribute new models, and it can do that by contributing entirely new models or by extending the properties of an existing model via inheritance. Now here is an example of one of our services. This is the virtual OLT service that manages Volta as well as the OLT abstraction, perhaps touching other components such as ONOS in the process. And you can see it's involved in a couple of chains here. The first is a service level chain. And this service level stuff has kind of global configuration for the service. So everything that is global and common across the entire virtual OLT service would go in its service model. And it is depended on by the rcord service, because the rcord service implements subscribers, and subscribers need OLTs and ONUs in order to have connectivity. And then the virtual OLT service itself just depends on the Fabric Cross Connect service, because those OLTs and ONUs need to get their packets out to the BNG. So you have a whole chain of dependency. One service depends on the next to get its work done. Now, that was global. There's also this per subscriber aspect to it. So you've got a subscriber object within the rcord service that has data related to just one subscriber. And that is that subscriber's point of presence in that rcord service. And that, in turn, depends on a certain point of presence inside the virtual OLT service. For example, we know that the subscriber has to have a particular ONU. So there will be a relationship to an ONU. And then that subscriber needs his packets specifically routed through the aggregation switch. So he has, for example, an S tag and a C tag. Via this next link in the chain, we will program his S tag and C tag to get through the aggregation switch out to the BNG. The other kind of models we have are these auxiliary models. They're all in green, and these are just additional service-specific models that are necessary for the service to inventory and glue together various objects. So this being the virtual OLT service, it has to know about things like OLT devices, ONU devices. The ONUs have UNI ports. There's a PON network that goes between OLTs and ONUs. and an NNI port attached to the OLT device. So just some basic modeling concepts. I'm not going to drill down into every service because we don't really have the time for that. I just wanted to kind of give an idea of what a typical XOS service looks like. Now, as I showed before, here you take this xproto service declaration, and that tells how to configure the data model. So the next part I'm going to break down is that. And xproto is our data model description language. And we use it to not only describe the data model, but it also contains additional information so we can auto-generate other artifacts in the system. It is based on Google Protobuf and extended with features such as relations, with inheritance, with additional syntax, and features like data validation, stuff like that. I'll show you an example and it'll become clear how we've extended it to have these additional features, because Protobuf itself is primarily describing data structure. We're also describing structure as well as a lot of semantics. So you can use this via a tool we wrote called XOS Gen X to auto-generate various targets in the system, such as the data model, the gRPC API, a structural declaration for the GUI so it knows what forms and stuff to draw on the screen, a command line interface. Via Chameleon, you get a REST API. And we think of this as when a developer needs to make a change, he needs to make it only in one spot, and all of this value is auto-generated, rather than having to make the same change in 6 different places, to have to touch schemas and stubs and GUI forms. It's all done for you to make the developer's life easier and to make service development faster. I have an example of xproto here. I'm not going to go in super detail in this, but I wanted to kind of give a feel for what it takes to describe a typical xproto model. And this is the ONU device model within the virtual OLT service. So it has a name, it's ONU device. It has inheritance. It inherits something called XOS base. That is sort of the base object that you can inherit out of the data model. There are other higher level objects as well it could have inherited from. So it gets all the fields from XOS base automatically. The verbose name is something that will show up in the GUI to describe it. Description is another field, is the human readable help text. If you're familiar with Protobuf, this should look very familiar, but you will see a lot of these extensions we've added. Whoops. So for example here, we've added this many to one keyword. That says that this next field here is a relation. So this is a required relation. An ONU device must be attached to a PON port. And it does this through a field called PON to the port. No, I said that backwards. Anyway, it's attached to the PON port via a field called PON, and it has a reverse field called ONU, and we have some protobuf numbering for that. You can see things like our strings have various things like maximum length, keys, uniqueness properties. There's help text for some of the fields. We can have choices. So you can have, a field will have a limited number of choices that's useful for validation and for display in the GUI. So a lot of this additional value is used in generating all of those additional artifacts. Now I'm going to talk a little bit about migration. And migration starts with the notion that the data model does have to evolve over time. So as we said at the beginning, our service stack is dynamic, that we do expect services to be upgraded as well as deleted or new services added. So new services can be added over time, old services can be removed. Existing services may be upgraded. Now, an upgrade of a service could use all of the same models, nothing may change, or an upgrade of a service could contain new models, or it could add new fields to existing models. You might even rename fields within models. So when the data model changes, usually that's manifested by people submitting new xproto to XOS, and it will reconfigure the data model. Service upgrades we expect to be commanded by the operator, and I'm going to dive into how the core handles this process of ingesting the new xproto and updating itself. So whenever you do data model migration in a database, there's two aspects to it. One of them is to migrate the schema. The schema is the structure of the database. You can think of a particular model in the database. You know, it has a name, it has 10 fields. The fields each have a name, and one is a string, one is an integer, etc. So you need to update that structure by adding, deleting, renaming fields within that structure. But you also need to update the live data in the database. And that is because we want to preserve the existing state in the database. We don't want to have the operator come reconfigure the system. We need to migrate that data from one version of the schema to another. And it's not necessarily a simple mechanical change. These changes can have semantic value to them. As an example, suppose version 1 of your model, a user had a first name and a last name, whereas version 2, you decided that the user should just have a single name and those should be combined. Well, someone has to go write some code someplace that says in version 2, the name field is equal to version 1's first name plus a space and version 1's last name. And the place where that will go is inside of a migration script. So Django, fortunately, has this migration support built into it. It has the ability for each time that you change the schema to also supply these migration scripts that describe how to make the changes to the schema as well as how to make the changes to the live data in the database. So that was very fortunate. Since we were using Django, we were able to use that feature almost exactly as it was implemented without having to change much. So as an XOS developer, you would be responsible for writing these migration scripts. Now we have created a tool called XOS Migrate that will auto-generate the script for you, provided there is no complexity that requires those complex semantic transformations. It's smart enough to figure out that you've added or deleted fields from a model or created new models. But if you want to do something like translating that first and last name into a single name, you've got to write a little bit of code and add it to the migration script. And upgrade is driven by those synchronizers. If you recall the picture, we had the XOS Core, and then beneath it were a bunch of service-specific synchronizer boxes. Each one of those synchronizers, when it comes up, it will supply the migration data to the core, telling the core how to update the data model.
XOS has Django DB, right? And then the NEM, I think when AT&T wrote the abstract OT, we are using the MongoDB. And then the Volta has the data store is the XCD.
Yeah, and then Micro ONOS has something else. So yeah, I can see where you're going with this. Everyone has chosen their own data model abstraction.
Right. And
So the question I guess you're probably getting at is, why do we have another one? Kind of?
or what is the best one?
Right. So one of
The best one is ours.
Yeah, one of the things to talk about with this is that because the NEM lives in a layer above ONOS and Volta and all the other components, and it contains all of the data that a service provider would have put into it. If you lose those components below, like for example, if we lose ONOS right now, XOS has the ability to, by looking at the Kubernetes components, see that ONOS is restarted, and then push all its config back into ONOS, having it rediscover whatever changes were needed to be made and reconfigure the system. So what this does is it lets us have a layer above, at the top, that provides configuration to below, and that gives us some ability to do ISSU to those components below.
But if every layer does persistence and recovery,
Right.
that point is a moot point.
Right. So the point is that if the layers above do that persistence and recovery, then the layers below don't need to take care of it. I realize that there may be some level of an outage there below, but
What was your version? Oh, we are fine. Oh, no, we are not fine. I missed the last record.
right.
So
So there are implementation details. I'll just say that
no, they are not.
well, no. How would you describe that?
Here, let me try to add
Go
some.
for it. Go for
So I think that every layer doing its own recovery is good for performance optimization. Each layer, if one component went down and came back up, it and it stored its state persistently, it can recover that bit of state itself just fine. XOS is the holder of authoritative state for the whole system. So what XOS is constantly doing is checking that everything matches the authoritative state. So it's not just to cover loss and restart of these components, though it can do that. It's to cover a divergence of what we expect the state to be. If something has malfunctioned, we can bring it into compliance with our declared desired state at the top.
What I was saying is, I just want to understand why there's so many different databases, and I'm sure different databases probably work differently for some reason. So let's let Scott continue his talk.
I would assume each component author chose theirs for a reason. Some of the reasons may have been familiarity, some maybe had a specific feature they wanted. We've ended up in the situation where everyone has their own, and we can talk in other contexts about maybe adopting a more uniform approach across projects and coalescing on a smaller set of persistent data storage solutions.
And I just want to inject that to wake everybody up, that's all.
Well, thank you, Sean. Let's see, where was I at? So I think I was down here at upgrade is driven by synchronizers. And the synchronizers, when you perform a service upgrade, they will supply whatever the core needs to know to do that upgrade. Each time we do this, the core stops, runs migration scripts, and then restarts. The way we've designed this, every synchronizer and every service knows about the other's models. So we kind of redistribute this knowledge throughout the various synchronizers. Now it's important to note that we can restart XOS without causing a loss of data plane connectivity because XOS is not actually in the data plane, it's in the control plane. So components that are handling the data plane like Volta and ONOS, they can continue to pass traffic while XOS is doing one of these migrations. And we will consider in the future approaches toward live migration to keep XOS running without disrupting it, because even the control plane, it would be nice to keep it continuously operating. So I'm going to walk through a few examples where we do some operations on services. So how do we bring up a new service? Well, it starts out by bringing up a new sync. I hate this trackpad. If I move my finger, sometimes it thinks I clicked when I did not. You bring up a new synchronizer. The first thing the new synchronizer does is register with the XOS core. It says, these are my models and these are the migration scripts. And it supplies a whole set of migration scripts all the way back to the initial case. So, you know, this was version 0 of my service. Here's version 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And I'm currently at 4. So the core ends up with a whole set of these migration scripts. No matter what version of the modeling the core has, it knows how to do that incremental change to get up to what this service says is current. The next thing that happens, the XOS core stops because we don't want to be processing traffic while we're in the middle of doing the database migration. It migrates the data model, then the core restarts, and it pushes those changes both to the synchronizer that requested them as well as all of the other synchronizers. The synchronizers internally will note that the data model has changed, and restart is necessary. So upgrading a service is similar, but what we do is we start by destroying the old synchronizer, and we bring up a new synchronizer in its place. The new synchronizer sends its models and migrations, so it sends its current models as well as migration scripts. If we were at version 4, there will be 0 to 1, 1 to 2, all the way up to 4, plus 4 to 5. So one additional migration script shows up. The XOS core stops, migrates the data model, restarts, pushes it all to the various synchronizers. Deleting a service. This one is a little bit different because in XOS you cannot simply delete objects from the data model. Because those objects may reference live stuff in other services, we actually require a deletion step to be run. And that deletion step lives in the synchronizer. So you can't just simply destroy a synchronizer and destroy its data at the same time. You need to destroy the data first, let those deletion steps run, and then you can destroy the synchronizer. So first you have to call this unload models API request. That'll go through, destroy all live data with that synchronizer. Or if you don't tell, you can also give it a flag that says, don't destroy anything, but fail if there is live data, and then you would be responsible for cleaning up yourself. So the result is, before you can proceed, all the live data needs to go away. Then you can destroy the synchronizer. Then the core can stop, migrate the data model, restart, push new data model to all synchronizers, and then begin servicing requests. And I think I'm ready to hand off to Zack for a few slides.
So how this is implemented internally, it's like the rest of SIBA. So we use Helm and Kubernetes. SIBA launches all its services in containers. So when you deploy that, you use Helm and install the services. All the services are packaged in a Helm chart, and Helm natively supports the upgraded charts. So when it comes time to upgrade, you tell it upgrade. You tell it there's a new driver image, so this would be a typical thing during a developer cycle of I'm going to upgrade my service, so I tell it to use a new tag, and it uses a new container you just compiled, and it tells you that you've been upgraded. And it's fairly straightforward. Helm terminates the old containers, starts the new container, and XOS does everything internally. There's really not a whole lot to it from a deployment perspective. So this integrates really well with existing Kubernetes and Helm-based deployment tools. They're fits well into that environment and doesn't require that an operator do fancy things, assuming that the versions are written correctly by the developer. And it's boring and uneventful in the ideal case, which is what people want: boring and uneventful. The service would go down, but that's the XOS service. So it's all control plane level things. Also, XOS has to restart, as Scott mentioned. So that portion of the control plane goes down, comes back up. We'll show doing an upgrade, we'll show doing a backup, which does take it up and down. It's a couple seconds, so maybe 30 seconds or a minute at most. So yeah. I think after this is the demo.
Yeah.
So are you ready to go there?
Well, let me ask Saurav. Is Saurav? I don't think he's handy. So I'm worried about our timing on the demo, whether we really have enough time to go into it in 5 minutes. Yeah, 5 minutes. I think what I may do is I may describe chord control and say some words about it and then open up for questions rather than actually doing a chord control demo, because that'll probably take a good 10 to 15 minutes. So we have written a tool called chord control. If there are Volta people here, you've probably heard of Volt control. And chord control actually shares some of the code base with Volt control. So we saw David had a great idea when he implemented Volt control, and we decided, well, we want to make a tool just like this. And I spent a lot of time with David learning how he did it so that we could do it ourselves. Chord control is a command line tool for managing the NEM via XOS. So it speaks that gRPC API to the XOS core. And you can do all kinds of things with it with interacting with models. And we actually did, during yesterday's tutorial session, we did, maybe 15, 20 minutes using chord control to look at various models, to update the service, the ATT workflow driver service, to add a whitelist entry, to delete a whitelist entry, a bunch of stuff like that. So what I'm going to try to do for people who are interested is that tutorial session was recorded, and I will find a link to that recording, and you guys can watch through that tutorial because it would be very similar to the one that I would do. Just to give you some of the ideas for what kinds of things you could do, there is the service inventory, the list of synchronizers. You could list those. You can list the various models that XOS supports, as well as you can list objects of the model type. You can create models. You can update models. You can delete models. And you can do this for any model that XOS knows about. So both the core models and the various service-specific models like RCord subscribers and ONU devices, all the ones I showed you in the Volt service, you could go in and touch those. And then we also have an interface to backup and restore. So because the XOS is considered a repository of authoritative state, we implemented a backup and restore feature built into XOS so that you can make an API call to XOS, say back up the data model, and XOS will perform the necessary steps to freeze the data model, back it up, give you a copy of it, download it to you. You can store it on your administrator's machine, and then you can restore it at a later time if you would prefer. So we encapsulated that functionality built into XOS. So I think that concludes the presentation. We're open for questions.
Thank you. So my question is on the data models. I want to understand if there is any relationship or one can make use of between the Cloud CO broadband forum, like the TR383, 385 Yang models, and the data models that you're talking about here. The xproto that you're talking about, can the Yang models defined over there be made use of over here?
So at one point, we had one of our developers wrote a tool that translated, just like when I showed you at the beginning, I showed you there was XOS, there were translators above it that we had one for Chameleon that translated to REST, one for Tosca that translated to Tosca. We did have someone who at one point was working on one that translated to and from Yang modeling. So we were looking at that capability. We were also looking at the capability with XOS Gen X for it to be able to both convert xproto into Yang models and perhaps be able to convert Yang models into xproto. We haven't had a need for that work in some time, so it kind of fell by the wayside, but it was something that we were working actively on at some point because just like people have developed different database backends, a lot of people have come up with different modeling choices, and it's nice to be able to converge and translate.
Do you see like tools like systems like NEM and Core CTL to be applicable only to SIBA or in the future also to other services? Like for example, if you're running like Trellis in the data center but not a SIBA and Volta infrastructure, but you're maybe running transport services and use it to manage, don't know, connectivity services for enterprise or things like that, VPNs.
Historically, it's because Core is extensible, and this just happens. We just happen to be giving you examples from SIBA. We've used Core with different services designed for enterprise use. We had an eCore initiative that provisioned those Metro Ethernet and those sorts of things. So this is extensible. It's a general purpose tool. Does that answer your question?
And furthermore, there were all of those service synchronizer boxes that were underneath XOS. Those are how you tailor XOS to various services. So there could be a Trellis box as well, or a Stratum box, and XOS would then be able to control and configure Trellis and Stratum.
Yes.
What is the purpose of card control? It's just the CLI, or because Volta has its own CLI, right? So is card control another CLI?
Yeah, it is a CLI for XOS specifically, whereas Volt Control is a CLI for Volta. And then ONOS presumably has their own CLI. So each tool has kind of developed a CLI to manage it.
So if I'm running some microservice, should I be implementing such a control for my microservice?
If you have a XOS service and you've created an xproto for it and loaded it into XOS, then Cord Control will expose a CLI for that, because Cord Control also interacts over gRPC by creating what is it? It's using gRPC reflection to generate its CLI on the fly. So all the models will just appear in Cord Control.
Thanks.
Yeah, so the only need to use something like Volt Control is if you have not fully extended your Volta abstractions into XOS. And maybe as a developer or debugger diagnostics, you needed to poke at something that was not exposed through XOS.
Right. Okay, thank you.
Thank you.